Hello there, Mr. Sutton here, bringing you the Algebra 2 10-3 lesson on trigonometric functions of any angle. This will be a two-parter. In this one, we will be evaluating trig functions, that's sine, cosine, tangent, secant, cosecant, cotan, whatever those are, given a point on an angle. And also, we're going to evaluate these same functions using the unit circle. And last but not least, we will be evaluating these functions using something called reference angles. We're going to start this lesson off with a question. What do you know about cosine, sine, and tan of theta? How are these defined based on what you've seen so far? So pause the video and give that some thought and write down what you know. Alright, so we've seen these all in the context of SOHCAHTOA. That was when we were solving right triangles for their sides and angles. So cosine, that was part of the ca part of SOHCAHTOA. That was adjacent over hypotenuse. Sine, you might remember, that was part of SO, opposite over hypotenuse. And tan, that was part of TOA, opposite over adjacent. Now we've only thought about these in the context of a triangle. But then we started thinking about angles in the context of circles when we were talking about degrees and radians. So we're going to bring all these things together. So here's a piece of a circle. And we're going to draw an angle on this, but we're going to relate it back to this stuff by actually turning that angle into a triangle. So we're just going to take the terminal ray here and drop an altitude down to the x-axis, and abracadabra, we've got a triangle. So this angle here, this terminal ray is hitting the circle at a certain x and y value. Now, if we think about this in terms of sides of a triangle, the x value, that's how far over you went to get there, left-right kind of distance. So this base of the triangle we can call x if we want. And the y value of this point, that's the height of this triangle, that's the y right here. And if we want to give the third side a name, well, this is the radius of a circle. It's halfway across a circle. So we're going to call this r. Now, we can actually express all of these trig functions in terms of x, y, and r, just on this whole opposite adjacent hypotenuse sort of scheme. So let's talk about cosine first. Since that's adjacent over hypotenuse, based off this angle, x is touching the angle. That's the adjacent side. So we would have x over the hypotenuse of r. So if you do have an angle touching a circle at a certain point, the x value divided by the radius is the cosine of whatever angle that is. Now we can do the same thing for sine and tangent. Sine is opposite over hypotenuse, so that's going to be y over r. And then finally for tangent, we can call that one opposite over adjacent, so opposite side y over adjacent side x. Now, we're actually going to get a little bit crazier with tangent. It is possible to rewrite this, and there's no reason you would think to do this normally, but we can do it. We could rewrite this, if we wanted to, as y over r divided by x over r. We could unsimplify it into this quotient if we wanted to. And again, there's no reason on heaven and earth you would actually do this, but it is possible if you wanted to. And if you want to see that this is legal, well, if we divided these, we would be doing y over r times the reciprocal r over x. R's would cancel, and we would indeed end up with y over x. Now, why would we actually do this? Well, y over r, where have we seen that before? Oh, we just saw it up here. That's what we're calling sine, y over r. So this y over r up here is sine. This x over r down here is cosine. So if we wanted to, we could think of tangent as sine over cosine. And we're going to see that there's times where it actually is pretty helpful to do that. If we know the sine and cosine of an angle, we can use that to figure out the tangent, even if we don't happen to know the radius of the angle. So let's take another step forward here. The title of this slide says there are 6 of these, and in fact there are. We've got the classical 3 trig functions here. They all have designated buttons on calculators, but it turns out there's 3 more trig functions that are reciprocals of these. So each trig function has a reciprocal function, and I want to be careful in how we're calling these. Reciprocal does not mean inverse. There are actually an inverse trig function for every single trig function we're going to see in this lesson, and that does not mean the same thing. The reciprocal function, we're basically taking whatever is up here and flipping it upside down. So there's a function called secant that is actually the reciprocal of cosine. It's 1 over cosine. Now because this is 1 over cosine, that means everything about cosine gets flipped. So secant is also hypotenuse over adjacent. It's also r over x, so everything is getting flipped. Now there's another function called cosecant, which is the reciprocal of sine. So this is 1 over sine, or we could call it hypotenuse over opposite, or we could call it r over y. And there's one more function, cotan. I'll bet you can guess which one this is the reciprocal of by process of elimination. Yes, this is 1 over tangent, which means that cotan is also expressible as adjacent over opposite, if you're thinking about this in terms of a triangle, or we can call this x over y, or we can call this cosine over sine if we wanted to. So all these are ways of talking about cotan. For the next few problems, we're basically going to be figuring out the value of all 6 trig functions in different situations. The first situation we're given is that they actually give us an angle with a point that it intersects either on some circle or just some random point. So our strategy on most of these is going to be to figure out the x, y, and r values involved in the problem and plug those into those 6 different trig formulas that we had that had x, y's, and r's in them. So I think we can figure out the x and y value from this one pretty quickly. Taking a look down here, what's our x value? Why, it's negative 12. And we have a y value of negative 9. So they basically spelled it out for us. Now this is good for the functions that have just x and y, but there's also some functions that have r's in them. So we're going to need to find that third variable. Now how can we find that third variable? Well, since this is all based off of a triangle, and in fact it's based off of a right triangle, that means if I have 2 sides of the triangle, which I basically do here, I have the height and the base of it, I can find the third side of a right triangle using the Pythagorean theorem. Now, in order to use the Pythagorean theorem in this context, we don't really have an a, b, and c. Instead, we have an x, y, and r is our hypotenuse. So we can use a version of the Pythagorean theorem called x squared plus y squared equals r squared. Let's go ahead and use this to figure out the radius of this thing. So if I want to get the radius, I need the x and the y, which I've already got here. So in that situation, I can just take the square root of both sides here and write r equals the square root of x squared plus y squared. So that's going to be the square root of negative 12 squared plus negative 9 squared. That's 144 plus 81, and I believe that comes out to 225, and we need the square root of that, and we're supposed to be able to do all of this without a calculator. So hopefully you know the square root of 225, which does happen to be 15. That's a good one to know. So at this point we've got our x, our y, and the r. Now I'm going to leave you on your own in a minute to plug these into all those different formulas. Just a couple of things when you do that. First off, they want the answers in simplest radical form. I don't think there's going to be any radicals on this problem, but part of that also includes having a fully reduced fraction. So make sure you're following all those rules. And the other piece is, just as a little bit of a tip, it's going to be more efficient if you find sine, cosine, and tangent first, and then once you've got those, you can just use reciprocals, basically flip those to get the other 3. So that might save you a couple of steps in terms of reducing and simplifying. So with all that said, pause the video and see if you can find all 6 trig functions of whatever this angle is using what we've got so far. Alright, let's go through it. So we'll start with sine. That's y over r. So in this case, that's negative 9 over 15, which I can reduce to negative 3 over 5. Next up, we've got cosine, which is x over r. So that's negative 12 over 15. reduces to negative 4 over 5. And finally, tan was y over x, which was in this case negative 9 over negative 12. And that reduces to positive 3/4. Now we said that all the other functions are reciprocals, so we can basically flip these three to get three more. Cosecant, that's the reciprocal of sine, that's r over y, so basically just negative 3/5 upside down, negative 5/3. Next up, secant was really r over x, the reciprocal of cosine. So flipping this, we have negative 5 over 4. And then finally, cotan was the reciprocal of tan, so x over y. So this reduced 3/4. We can just flip that final reduced answer to get 4/3. For this next problem, we are given the sine of an angle, and they're telling us it's negative 7/10. And they're also telling us that the angle is between pi and 3 pi over 2. So the basic idea here is they're giving us one value of the trig functions, and they're also giving us the quadrant that our angle is in, and they're asking us to find the other 5 trig functions based off of that. So the general strategy is going to be the same. We still need x, y, and r to get all of those functions. This is a little bit trickier though, because they're not explicitly telling us what x and y are, or even r. So we can figure that out based on the information they gave us, but we're going to have to kind of tease it out of that information. The other thing we need to be aware of is that, some of these things can be positive and negative. So now, specifically, out of those three things, x, y, and r, the radius, is always going to be positive. It's just how far you are from the center of a circle. So if we have to choose between, something being negative and r being negative, we're going to choose the something else. R is always positive, which means x and y, those can be negative or positive, right? Based on where you are with respect to the x and the y axis. So the way that we're going to figure those out, we're going to use the quadrant that we're in, which they're telling us here, to determine the sign of x and y. And we'll actually do that together on this one. So if my angle is between pi and 3 pi over 2, well, that's between 180 and 270. So if you just kind of visualize your unit circle, or your circle, that is going to be between like the left x-axis and the bottom y-axis. That's the third quadrant, lower left. So in that quadrant, in the lower left, x is negative and y is negative. And it's typically a good idea to figure out what the sign of x and y is going to be before you go any further in the problem, because you're going to need this as we go. So once we've established that, we're going to start finding x, y, and r. So once we've got two of these, we can use them with the Pythagorean theorem to figure out the third variable. That's not going to change from what we've already done. But finding those first two is a little tricky. And it comes down to this function that they've given us here. We're going to use the formula of the given function to find those first two variables. They're giving us the sine of an angle here. Well, what's the formula for sine of theta? You might remember that that's y over r. So if sine is y over r, then that means y over r equals negative 7 over 10, which means that y is either 7 or negative 7, and r is either 10 or negative 10, right? We have to kind of figure this out. Now this is where it's helpful to know, first off, that r is always positive, so we know if something here is negative, it's not the r, it's got to be the y. But also we saw here that we're in quadrant 3, and we know that y is negative down there. So from this we can conclude that y must be negative 7, and then r has to be a positive 10. R is always positive. So based off of this, we can now use Pythagorean theorem, figure out our third variable, and kind of go from there figuring everything else out. So with that in mind, pause the video and see if you can figure out x and the other 5 trig functions based off of that. Alright, let's see how that went. So our general Pythagorean theorem, we've got x squared plus y squared equals r squared. In this case, we're looking for x squared. So I need to do r squared minus y squared and then square root that. So I'm going to have the square root of 10 squared minus negative 7 squared. That's 100 minus 49, which is 51, so we have the square root of 51. Now we mentioned up here that x is negative. So I'm actually going to write negative 51 here. So you got to be careful. Once you take that square root, you have to choose between a positive and negative typically. Now let's plug this and all these other values into our 5 trig functions. So we would start with sine, but sine's already taken care of. We've got negative 7 over 10. That's great. So let's move on to cosine, which again was x over r. So in this case, we found the x value negative radical 51, and we have the r value 10, so negative root 51 over 10. All right, that's pretty straightforward. That's as simplified as that gets. Let's move on to tangent, y over x. So we've got the y value negative 7 over the x value negative radical 51. A few things I can do to simplify this. First off, I have a negative divided by negative, so that's going to come out to a positive. Also, this square root down here, we never want to leave it like that. I'm going to multiply this by radical 51 over radical 51. So this will be positive 7 root 51 over positive 51 when the dust settles on that. That is going to be simplest radical form. Now for the rest of these, I'm going to go ahead and just flip the original 3 functions. So for cosecant, that was again going to be r over y, so basically just flip the sign up here, and that gives us negative 10 over 7. Let's see, secant was r over x, the flip of cosine, so that's going to be negative 10 over radical 51, but now we have a radical in the denominator, got to take care of that. So this is going to be negative 10 root 51 over 51. And then finally, we have to take tangent and flip it upside down to get cotangent. So that's going to be negative radical 51 over negative radical 7, which we can just make positive root 51 over positive 7. And that's all of them. So up to this point, they've been giving me kind of specific circles to find trig function values on. And those circles have been of various sizes, I would say shapes, but all circles actually have the same shape. It turns out all circles are similar, it's just they have different proportions, same shape though. Because all circles are similar, if they don't give me a specific circle to work with, let's say they're just asking for like the sine of some angle, and I'm allowed to choose my circle, which circle should I choose? Well, the good news is, since all circles are similar, that means that the simplified trig values at some angle are actually going to be the same for all circles. If I try to find the sine of some angle on some circle and I get 6 over 10, and maybe a circle like half as big I get 3 over 5, well, that's really the same value. It's just the proportions were different. So it turns out that since the trig values are going to be the same for all circles, if I'm allowed to choose a circle, maybe I should pick a circle that's going to be like the easiest circle in the world to deal with. What circle would that be? At this point, I'm going to introduce to you my favorite circle, the unit circle. Now, what does the unit circle actually mean? Well, unit is from the word unity, which means kind of oneness, and that goes with what the definition is. The unit circle is just a circle that has a radius of 1. Now, why would this be such a big deal? I mean, it's a pretty simple circle, but who cares about a radius of 1? Well, it turns out this makes it very easy to figure out the cosine and sine, because on the unit circle, cosine we've seen a few times now is x over r. But if your radius, if your r is just 1, well, what's x over 1? It's just x. So on the unit circle, we can simplify the cosine to just be whatever the x value is on that circle. And by the same token, since sine is just y over r, that means that sine on the unit circle is just y. So if I'm looking for the cosine or sine of some angle, and I'm allowed to choose any circle, you do you, but I'm doing the unit circle, right? Because I just have to find the x or the y value of the angle, and I've got my answer. Now, while we're talking about really simple things, this is not just the unit circle, but for all circles. Tangent, you might remember, is y over x. That's really like having rise over run. So tangent, it turns out, this is actually kind of a big thing, is the slope of the angle. And this idea of tangent being the slope actually keeps coming back over and over again. You might have seen tangent lines when you were looking at circles back in geometry. A tangent line just touches a circle in one spot. It turns out the slope of a tangent line is the slope of the circle at that one spot. So tangent and slope go hand in hand. That's a good one to remember. All right, with this background, we are now going to use the unit circle to find 6 trig functions for theta at the angle 270 degrees. So what is sine of 270, cosine of 270, secant of 270, all of those. So just a few little tips for doing this. First off, I would recommend you actually draw the angle out, whatever it is, to allow you to find x and y. Remember, with cosine and sine, you're just looking for x and y of the angle. So if you can see that just by drawing the angle on the unit circle, which again goes 1 in every direction, that will make your life a lot easier. And just remember when you do this, again, the x is the cosine and the y is the sine. It's actually easy to remember because it goes alphabetically. X comes before y, and then alphabetically, cosine comes before sine. Now, once you've got the cosine and sine, which you're going to find on your own in a minute, all the other trig functions are just some fraction combination of cosine and or sine. So you can actually use cosine and sine values that you get here to find the other 4 functions. So that's a big hint of the direction you need to take on this problem. Pause the video, draw this thing out, find x and y, and find everything else, and let's see where we end up. All right, so 270 degrees. Here is our unit circle, and this goes 1 in every direction. 270 is down here, so there's our angle. And specifically, we need to know the point at which this hits the circle. Since it's the unit circle and goes 1 in every direction, we know that the y value down here then must be -1, and the x value, since we're on the y-axis, has to be 0. So this is the point 0, -1. It's probably worth writing that down so you can use it to find your cosine and sine. Based off of that, we can say that our sine, which is the y value, is -1. And there's no reason I wrote sine before cosine, but you could write cosine first. It doesn't really matter the order you find these in. The cosine is the x value of this point, so that's going to be 0. And now to find my other 4 trig functions, again, they're just combinations of sine and cosine. Tangent, for example, that's just sine over cosine. Well, I already figured out both of those. So that's just going to be -1 over 0. Now, if we divide by 0, the rules are the same as they've always been. You can't divide by 0. So this actually is undefined. And in fact, we see that any of these trig functions that can be expressed as fractions with sine and cosine, they can all be undefined in different situations. So you kind of have to be on the lookout for that. The next one we'll find is cosine, or cosecant rather, which is the reciprocal of sine. Since I've already got sine figured out, I just need to do 1 over sine to get cosecant. So that's 1 over -1, or -1. Next up, we'll do secant, the reciprocal of cosine. Well, 1 over cosine in this situation means 1 over 0. That goes the way of tangent here. That's just undefined. And then finally, cotan. We can express that a few ways, but since I've got sine and cosine, let me just do it this way. So cosine over sine, that's cotan. That's going to be 0 over -1, which comes out to 0. Now, I could have thought of this as, well, it would be a little bit tricky. This is the reciprocal of tangent, so I could think of this as 1 over undefined, but honestly, what does that mean, right? So in this situation, definitely cosine over sine is a little bit easier to work with. So at this point, we have reached the end of part 1 of this lesson. Up to this point, we've figured out how to find the 6 trig functions on non-unit circles, and we've also figured out how to find the trig functions on a unit circle if we give you one of these easy quadrantal angles where you can read it right off the circle, where you know that the x and the y values are all going to be either 0, 1, or -1. But what happens if we have kind of one of these in-betweener angles? We'll deal with that in part 2. Until then, Mr. Sutton temporarily signing off. Welcome back to part 2 of this lesson on finding trigonometric functions of any angle. That's kind of, that's a big claim to be able to do this at any angle. Right now we can only do quadrantal angles. So we're going to expand our horizons a little bit in that respect. In order to do this, though, we're going to need a new concept, a new type of angle called a reference angle. So we're going to start this part of the lesson by figuring out how to find these. So here they're saying sketch the angle and then find its reference angle, which we're calling theta prime. So sketching these angles, we've done this sort of thing before. But what's this whole reference angle business? So the reference angle, just to define it for us here, and this also kind of tells us how to find it. A reference angle is the acute, that's a 0 to 90 degree angle between your terminal ray and your x-axis. Now, sometimes the angle between the terminal ray and the x-axis already is between 0 and 90. Like if you're in that first quadrant, then you've already kind of got a reference angle. But let's say you're over in quadrant 2. So we're talking about the angle between your terminal ray and the left side of the x-axis in that case. All right, so you're using different parts of the x-axis depending on where your angle is. So with that in mind, we're going to find these two reference angles. Just a couple of tips for doing this. First off, I would recommend that you convert to degrees and put these in standard position first so you can figure out where you are. You're going to need to do that in order to sketch the angle anyway, but I would recommend doing this even if you're not officially required to sketch the angle, because it turns out knowing where your angle is really half the battle to figuring out what the reference angle is. So once you have sketched out each of these, the way to actually find the reference angle, since we need the acute angle between your terminal ray and the x-axis, you're basically just going to subtract your angle that they gave you. You're going to subtract the closest x-axis angle from your angle, or you're going to subtract your angle from the closest x-axis angle. So subtract possibly from the closest x-axis angle. And, which way do you subtract? Well, it all boils down to what's the bigger angle. You're just going to do bigger angle minus smaller angle to get the distance between your angle and the closest x-axis angle. So with all of that said, pause the video and see if you can decipher what I was just talking about there to figure out these reference angles. All right, let's start with part A. We're going to convert this to degrees first to make it a little easier to look at. So a little trick you can use if you're just kind of doing this in your head, you would be multiplying by 180 over pi. One way to do this quickly, though, is just say, okay, 180 divided by 3 would be what? Oh, 180 divided by 3 is 60. And then 5 times 60, well, that would give me 300. So basically divide by the denominator, multiply by the numerator, and those pi's are getting canceled along the way anyway. So 300. This is in degrees. It's also in standard position. It's between 0 and 360. So let's graph this out. This is going to be somewhere between 270 and 360. And I mean, graph it as accurately as you can, but as long as you get it in the correct quadrant, you're good for the next step, which is you're going to have to subtract your angle with the closest x-axis angle. So here we see that we are closest to the 0 or the 360 line. Because reference angles need to be between 0 and 90, I need to subtract with whichever one of these is going to give me a number between 0 and 90. 300 minus 0 is great, but it doesn't give me something in this range. Instead, then, I have to do 360 minus 300. Whatever gives me a number between 0 and 90, that's an x-axis angle. So this gives me 60 degrees. That's my reference angle for this one. That is this acute angle. Now for this next one, negative 130, we're already in degrees, which is a great start, but we're not in standard position. We want to be between 0 and 360. So I am going to add 360 to negative 130. That's going to give me 230, and that's a standard position angle that I can now put on my unit circle and figure out where I am. So 230 is between 180 and 270, somewhere in this area. And I see that I am closest to the 180 line in terms of the x-axis. So my reference angle then is the distance from 180 to 230, or 230 minus 180. And that's going to give me 50 degrees. So the ability to find reference angles is kind of half of the puzzle when you're trying to figure out values of non-quadrantal angles, but it isn't the whole picture. We need something else. So that something else is some special values of cosine and sine. There are three special angles, 30, 45 degrees, and 60 degrees. And what makes these special is that the cosine and the sine of these angles can actually be found using special right triangles. If you start with a special right triangle that has one of these angles in it and it has a radius of 1, it turns out you can get the values of cosine and sine of all three of these angles. We're not going to do that. I'm just saying you could do it if you want to. In practice, most people just memorize the values in the table below, but I just wanted to share this, that's where these values are coming from. So this is a table worth copying down and memorizing if you can, or at least be able to recreate it. So we have cosine and sine of 30, 45 degrees, and 60 degrees. So the trick for filling out this table, tips for memorizing these, first off, all of these are going to be the square root of some number over 2. So that already tells us your denominator is always 2. So this is a 2, this is a 2, we've got a 2 here, a 2 here, a 2 here, a 2 here. So if you take the cosine or sine of one of these and you don't get a 2 in the denominator, you clearly did not memorize this table. Alright, so how about this numerator? I mean, this could be a lot of different numbers, right? So what numbers could be in here? It turns out that we're always going to be taking the square root of a number between 1 and 3. The square root of 1 to 3. The way this works is that cosine starts up at 3 and we count down from there. So this up here is the square root of 3 over 2. So cosine of 45 is the square root of 2 over 2. And cosine of 60 is the square root of 1 over 2. But the square root of 1 is just 1, so we don't bother writing the square root symbol there. Now the good news is that for sine we actually use the same numbers, we just go the other direction. So we count up from 1 if we're doing sine of these different angles. So we've got a 1, square root of 2, and now this down here is going to be square root of 3. So these are definitely worth memorizing. You might be wondering why. I mean, this is only like 6 different trig values out of the infinite number that we could throw at you. But is it really? Cosine of 30 gets you radical 3 over 2, but 30, you might think, well, hold on a sec. We could also express that as cosine of pi over 6, right? Because that's 30 in radians. We could also express this as cosine of 390, because if I subtract 360 from 390, I get 30. So it turns out each of these, there's actually an infinite number of angles that could be rewritten as 30, 45, or 60. And then we could use these values to get the cosine and the sine of those angles. And there's more. It turns out that using reference angles, we can express a whole bunch of other angles in quadrants 2, 3, and 4 as these different angles. More on that in just a moment. Alright, at this point we're going to pull it all together, all those reference angles and special values, and see how all these pieces of the puzzle fit together to let us take, for example, the cosine of 330 degrees without using our calculators. So we're going to go through this first one completely together, and then I'll give you a few to try more or less on your own. So first off, let's review what we already can do. We can already find cosine and sine of our quadrantal angles. Again, that's your numbers between the quadrants, 0, 90, 180, 270, 360, pi, 2 pi, basically every version of these 4 different angles that you can think of. We can figure them out by just drawing them out and figuring out what x and y are. And that'll be enough. But how about the non-quadrantal angles? So for the cosine and sine of non-quadrantal angles, we've got a little bit of a process we're going to follow here. And once we figure out cosine and sine, here's the best part. All the other trig functions are really just cosine and sine in different forms. So once we've got these two and we know pretty much everything about these, we can use them to get all the rest. So first step in this process, a good first step would be to rewrite and draw your angle in degrees, if it's not already in degrees, and in standard position, just as if you were going to figure out the reference angle, which you actually are going to do in a minute. So we've got 330 right here. That is already in degrees. It's already a number between 0 and 360, so we don't have to rewrite this at all. We can just use 330 as is. So let's go ahead and draw that out. So that's going to be between 270 and 360. Now, I recommend drawing out your angle every single time you do one of these. Whether you do a quadrantal or non-quadrantal, you really should draw out the angle every time. In this situation, this is going to do two very helpful things for you. One of those things is it's going to help you with your next step, which is to determine the sine of the trig function based off of the angle's quadrant. It's also going to help you find the reference angle. But in order to make use of reference angles, we need to know what the final sine of the answer is going to be. Because reference angles are always between 0 and 90, and if you just take sine and cosine of something between 0 and 90, you always get a positive. But you should not always get a positive when you take cosine and sine of things that are bigger than 90. So taking a look now at this quadrant, we're in quadrant 4 for 330 degrees, and we're trying to find the cosine. Now when I'm figuring out the sine of the trig function, I'm basically asking, is x, if I'm talking about cosine, or y, if I'm talking about sine, is x or y positive or negative in this quadrant? Well, let's think for a minute. Cosine is x. Is x positive or negative over here? Well, we're to the right of the y-axis, so cosine x would be positive over here. Alright, so we know that whatever my answer is, it better be a positive number. Our next step, once we've figured out the sine of our final answer, is we are going to, using that correct sign, rewrite this expression with a reference angle. And this is another reason it's good to draw these, is it's going to make it a lot easier for you to figure out what you need to do to find the reference angle. In this case, we are closest to the 360 line, so that tells us we need to do 360 minus the angle, 360 minus 330, which is 30. So putting it all together, this is going to be positive cosine of 30. Once you've got this thing rewritten with a reference angle, hopefully it's one of your three special angles, 30, 45, or 60. If it is, you can use your special angle value to get the final answer. So you might remember that cosine of 30 was radical 3 over 2. Again, good to have those memorized. So this then would be positive root 3 over 2. Now you might be wondering a few what ifs. What if this were like cosine of 210 and it was over here? Well, then the cosine would have been negative and this would have been negative radical 3 over 2. Another common what if I get on this kind of question is, what if I do my little dance here and the angle that I get is not 30, 45, or 60? What if it's like 50 or 70 or something like that? Well, then one of two things happened. One is you might have messed up when you were calculating the reference angle. The other is your math teacher might have messed up and given you a problem that could not actually be done without technology. So the good news, bad news kind of thing is, in order to do any of these without technology, we need to give you an angle that's either a quadrantal angle or that you can rewrite as 30, 45, or 60. So if you don't get one of those, be very suspicious. So with that whole process in mind, maybe take a minute to review what we did with that cosine problem in the last example, and then pause the video and see if you can figure out the sine of 5 pi over 4 without using technology. Alright, so this time around we have something that is in radians, so we're going to want to convert that to degrees. 180 divided by 4 is 45. Good to know those factors of 180. And 5 times 45 is 225. So sine of 225. That is in standard position. That's between 0 and 360. So let's graph that out. So that's going to be between 180 and 270, exactly halfway between. So that means, since we're talking about sine, that's y values. Y values over here were below the x-axis, so y values are going to be negative in quadrant 3. So the reference angle now, since I'm closest to the 180 line, I've got 225 minus 180. That gives me 45. So I can rewrite this as negative sine of 45. And we know that the sine of 45 is root 2 over 2, so this is negative root 2 over 2. For our next problem, we're trying to figure out the tan of negative 240 degrees. So this has a few things going on with it, and I'll let you try it on your own in just a moment. But one thing you're going to find once you've done this problem, even if you're doing it pretty much correctly the whole way through, at some point you're going to be trying to figure out the tan of a 30, a 45, or a 60. And you're going to be like, wait a second, Mr. Sutton, I don't have any values, any special values of tangent. And that's okay, because tangent, cosecant, secant, cotangent, they are all based on sine and cosine if you look back at those formulas. So if you do get tan of some special value, you can work around that by rewriting tan, secant, cosecant, or cotan in terms of sine and cosine. And just using the special values for sine and cosine, it's going to be kind of ugly. You're going to end up with some kind of fraction that you need to figure out. But that will at least get you part of the way there. So with that in mind, pause the video and get as far as you can on this one. Alright, so first thing I'm noticing here is that I've got something that's not in standard position. It's a negative angle. So let me add 360 to that and get something between 0 and 360. Negative 240 plus 360 is going to give me 120. So I've got tan of 120. I can graph that out now. 120 is between 90 and 180, so it's like right about here. So in terms of the sine of tangent right here, there's a few ways you can reason this out. One of them is that tan is really y over x. The y value is positive here, the x value is negative. Since I'm dividing in their different signs, that tells me that tan would have to be negative right there. Another way you could have figured this out, you might remember I mentioned that tangent is the slope of the angle. If you remember that tangent is the slope, the rise over run, the y over x, this is a negative sloping angle, so that would also indicate that tan should be negative there. Alright, so once we figured that out, let's get our reference angle. 120 is closest to the 180 line, so we need to do 180 minus 120 for the reference angle. So that's going to be 60. So then when the dust settles, we've got negative tan of 60 degrees. And we're feeling great about ourselves. But this is the point that I said you would get to, where you've got tan or one of these other trig functions with a special angle that you don't actually have the value for. So we're going to split this up into sine and cosine. So you might remember, if you looked back, that tangent is really sine over cosine. So we can then rewrite this as negative sine of 60 over cosine of 60. And the good news is we have special values for both of those. So let's see here. We got the sine of 60. From our table, we know that that is going to be root 3 over 2. So we'll put that in our big complex fraction here. Cosine of 60 is a little bit nicer. That one is 1 over 2. Again, so nice to have these memorized. Fortunately, we've done this fraction divided by a fraction situation before. We'll just multiply by the reciprocal. So this is negative radical 3 over 2 times 2 over 1. These 2's are going to cancel, so conveniently that just comes out to negative radical 3. So this is a little bit of a dance every time you're trying to find the tangent of something. There is one value of tangent that's kind of handy to have memorized, and it's pretty easy to figure out. why it is what it is. Tan of 45, it turns out, is 1. Worth memorizing, but if you're really questioning whether this can be a thing, just consider that tan of 45 would be sine of 45 over cosine of 45, and those are both root 2 over 2. So if you take something and divide it by itself, you're going to get 1. But it's, nicer just to have that memorized and get there without all the hoopla here. All right, congratulations if you've made it this far. We've got one more final boss battle for you. This one, you've got the cosecant of 17 pi over 6. Pause the video and see what you can do with this one. All right, so just like all those other problems, if it's in radians, it's a good idea to convert that into degrees to make it easier to graph and figure out reference angles and all those things. So 180 divided by 6, that's going to be 30, and then 30 times 17, well, 3 times 17 would be 51, so that would be 510 degrees. And that's not in standard position. This is not between 0 and 360. So let me subtract 360 from that. That's going to be, well, let me think. 510 minus 300 would be 210, minus another 60, we've got 150. So cosecant of 150. That I can put on the unit circle. So that's going to be between 90 and 180, right about here. Now, cosecant is based off of sine, right? That's really 1 over sine. Sine is a y value. Y values are positive up here. So that means that cosecant, the reciprocal of sine, is also going to be positive up there. And in general, the reciprocal functions, cosecant, secant, cotangent, they are positive or negative wherever their reciprocal counterparts are positive or negative. So that's how I do that sort of reasoning, is look at kind of the original function of sine. All right, so let's get our reference angle. We're closest to the 180 line here. So 180 minus 150, that would be 30. So this would be positive cosecant of 30. Now, I don't know the cosecant of 30, but this is really just 1 over sine. And I do know the sine of 30. Sine of 30 is 1/2. So this is 1 over 1/2. And again, same change flip. We've got 1 times 2 over 1, which is just 2. So that is it for this lesson. Till next time, Mr. Sutton signing off. Till next time, have a good one.